93 million miles, the distance from the Earth to the Sun. 238,000 miles, the distance from the Earth to the Moon. These numbers, seemingly arbitrary, are critical in shaping the delicate balance that sustains life on our planet. The precise positioning of Earth within the solar system is no coincidence. In our solar system, the Earth's orbit around the Sun places it in the habitable zone, a narrow region where temperatures allow for liquid water, an essential ingredient for life. Even slight variations in the distance could lead to drastically different outcomes. If the Earth were just 5% closer to the Sun, temperatures could rise to levels where oceans might boil away, transforming our planet into a scorched, barren desert. Conversely, if the Earth were 5% farther from the Sun, our world might be a frozen wasteland, incapable of supporting liquid water. The gravitational pull of the Moon stabilizes the Earth's axial tilt, which in turn regulates our climate and seasons. This intricate dance of celestial bodies creates an environment where conditions remain stable and predictable, an environment where life can thrive. If the Moon was significantly farther from Earth, its gravitational influence would weaken, leading to unstable axial tilt and chaotic climate variations. Without this stability, the seasons would become extreme, possibly preventing the development of the stable environments needed for complex evolution to occur. Moving 444 million away from Earth, we find Jupiter. This giant planet acts as a cosmic shield for Earth. Its massive gravitational field captures or deflects many comets and asteroids that might otherwise impact our planet. Without its massive gravitational presence, the inner solar system would be bombarded by asteroids and comets, potentially causing frequent and devastating impacts. Such events could disrupt planetary systems, altering their composition and dynamics in unpredictable ways. When we expand further, we see another layer of precision. Our solar system is located in a relatively quiet and stable region of the Milky Way galaxy, far from the chaotic and dangerous central regions where supernovae and black holes dominate. This positioning within the galactic habitable zone shields us from excessive cosmic radiation and gravitational disturbances, allowing the solar system to maintain its structure. And on a much grander scale, the universe itself operates on finely tuned constants and physical laws. Consider the force of gravity. If gravity was slightly stronger, stars would burn out much more quickly, exhausting their fuel before they have a chance to form planetary systems. The rapid collapse of matter would lead to a universe dominated by black holes and neutron stars, leaving little room for the development of the diverse cosmic structures we observe. On the other hand, if gravity were weaker, matter would not coalesce efficiently, preventing the formation of stars and galaxies altogether. The masses of subatomic particles, such as protons and neutrons, also precise. If the mass of the proton was slightly different, the balance between protons and neutrons in atomic nuclei would be altered, affecting the stability of atoms. For instance, if protons were significantly heavier, they might decay more rapidly, leading to the instability of matter itself. Alternatively, if neutrons were lighter, atomic nuclei would not hold together, preventing the formation of the elements essential for the development of stars and planets. All other constants and law in our universe are also set at values that allow for the formation of galaxies, stars, and planetary systems. Even slight change in any of these values would result in a universe that is vastly different from the one we inhabit. A universe that might be devoid of galaxies, stars, planets, and the complex structures we observe. A universe without the delicate balance required for the emergence of life. A universe without us. So, how did this intricate balance come to exist? What is the origin of these precise configurations that govern the solar system, the galaxy, and the entire universe? Are these perfect conditions a result of random chance, an inherent necessity, or some underlying design? Could such fine-tuning be purely coincidental, or does it suggest a deeper, more profound order to the cosmos? $13.8 billion years ago, the universe began with a very tiny point. It was so small that if you tried to measure it, you'd need a ruler. So precise, it could count the hairs on a bacterium's back. Imagine holding a speck of dust on your fingertip, then shrinking that speck down until it was 1 billion times smaller. That still wouldn't come close to the scale of the singularity. Yet, it contained all the energy, matter, and potential of the entire cosmos. Within this minuscule point resided the seeds of all galaxies, stars, planets, and life itself. The singularity was not just minuscule, but also unimaginably hot and dense. It was so incredibly hot that the temperatures reached trillions of degrees. The heat was so intense that atoms couldn't exist. Even protons and neutrons were melted into a hot, dense soup of fundamental particles and energy. If you could somehow withstand the heat and observe this singularity, you wouldn't see anything solid or familiar, just a blinding, seething cauldron of raw energy and primordial particles. In terms of density, the singularity was a place where all concepts of density we know break down. In fact, the density was so great that the fabric of space and time itself was curved to an infinite degree. Matter and energy were packed so tightly together that the laws of physics as we know them couldn't even describe the conditions. This tiny, incredibly hot and dense point marked the beginning of everything. It was the ultimate paradox, a point of such insignificance in size, yet of infinite significance in potential. In that one tiny, incomprehensible point was everything, just waiting to begin. But this singularity was also incredibly unstable. The immense energy density and extreme temperature meant that it couldn't remain in this state for long. Then, in an instant, this instability triggered the expansion we now call the Big Bang. Contrary to its name, the Big Bang was not an explosion in space. Rather, it was an explosion of space. The universe itself started to grow from this initial point, and with it, time began. It was a rapid expansion where space itself stretched and expanded, taking the primordial particles and energy along with it. But the Big Bang was just the beginning of the story. Almost immediately after the Big Bang, the universe underwent an even more extraordinary phase of growth known as cosmic inflation. This period of inflation only happened in a fraction of a second, but had profound effects. The process of cosmic inflation can be likened to blowing up a balloon, where tiny bumps and imperfections on the surface get ironed out as it inflates. Similarly, any initial clumps or irregularities in the early universe were stretched out, resulting in the smooth and homogeneous cosmos we observe today. This smoothing effect was not just a random stroke of luck. It was an incredibly precise and delicate process. Consider the expansion rate of the universe during this inflationary period. If this rate had deviated by even a minuscule fraction, the consequences would have been catastrophic. For instance, if the expansion rate 1 second after the Big Bang had been smaller, the universe would have collapsed back on itself before it ever had a chance to expand. On the flip side, if the expansion rate had been larger by the same fraction, matter would have spread out too quickly, preventing the formation of galaxies, stars, and planets later on. As the universe continued to expand, fundamental forces began to differentiate from one another. These include gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The strengths of these forces had to be just right for the universe to develop as it did. For instance, if the strong nuclear force was slightly weaker, atomic nuclei wouldn't hold together, and atoms as we know them wouldn't exist. If it was slightly stronger, stars would burn out too quickly, preventing the long-term stability needed for life to evolve. During this early stages of the universe, fundamental particles such as quarks and electrons began to form. These particles combined to create protons and neutrons, which then fused to form the first atomic nuclei in a process known as nucleosynthesis. The ratio of protons to neutrons at this stage was crucial. If there had been a significant imbalance, the universe would have been dominated by either hydrogen or helium, preventing the formation of heavier elements essential for life. This period of nucleosynthesis lasted only a few minutes, yet it set the chemical foundation for everything that followed. As the universe continued to expand further, it reached a critical point known as recombination. During recombination, protons and electrons combined to form neutral hydrogen atoms. This process allowed photons to travel freely, leading to the release of the cosmic microwave background radiation, which we can still observe today. At this time, the universe also underwent a cool-down process. The rate at which the universe cooled was vital. If it had cooled too quickly or too slowly, it would have disrupted the formation of atoms and the subsequent development of cosmic structures. As the universe continued to expand and cool, it eventually reached a point where electrons could combine with nuclei to form neutral atoms. This occurred about 380,000 years after the Big Bang. The timing of recombination was crucial. If it had happened too early or too late, the distribution of matter and radiation in the universe would have been significantly different. Before recombination, the universe was opaque because free electrons scattered photons or light particles, preventing them from traveling freely. After recombination, photons could travel unhindered, leading to the release of the cosmic microwave background radiation. The CMB provides a snapshot of the universe at this early stage, showing tiny fluctuations in temperature that correspond to the seeds of future galaxy formation. The uniformity and tiny variations in the CMB temperature are a testament to the delicate balance achieved during this period. Following recombination, the universe entered a period known as the Dark Ages, lasting until about 150 million to 1 billion years after the Big Bang. During this time, there were no stars or galaxies, and the universe was filled with neutral hydrogen. The rate of cooling and the initial density fluctuations, both remnants of inflation, were finely balanced to allow gravitational forces to amplify these fluctuations, eventually leading to the collapse of matter into the first stars and galaxies. If the density fluctuations had been larger or smaller, the structure of the universe would have been vastly different. Gradually, small density fluctuations amplified by gravitational attraction began to collapse, forming the first stars and galaxies. This period is known as the era of reionization, as the ultraviolet light from the first stars ionized the surrounding hydrogen gas, making the universe transparent to ultraviolet light. The timing and intensity of reionization were critical in shaping the development of large-scale structures. Dark matter, a mysterious form of matter that does not emit light or energy, played a significant role during this period. Though invisible, dark matter exerts gravitational forces, and its presence acted as a scaffolding for visible matter. Without dark matter, galaxies and larger structures might not have formed as they did. The precise distribution and amount of dark matter were essential for the universe's structural evolution. Dark energy, another mysterious component of the cosmos, began to influence the universe's expansion in its later stages. Dark energy is a force that drives the accelerated expansion of the universe. Its influence has grown over time, shaping the universe's expansion rate. The balance between dark matter and dark energy is yet another example of fine-tuning. If dark energy had been stronger or weaker, it could have prevented the formation of galaxies or caused the universe to expand too rapidly for structures to hold together. The period known as the Cosmic Dawn marks the formation of the first stars. Matter clumped together under the influence of gravity, leading to the birth of stars. The strength of gravity, perfectly tuned, allowed these stars to form. If gravity was slightly weaker, matter wouldn't have clumped together and stars wouldn't have ignited. If it was stronger, the universe might have collapsed before stars had a chance to form. These first stars underwent life cycles that included supernova, explosions that spread heavier elements throughout the universe. These elements are crucial for the formation of planets and eventually, life. Stars gravitated toward each other, forming galaxies. The formation of galaxies required a fine balance of gravitational forces and the universe's expansion rate. Hubble's law, which describes the rate at which galaxies move apart, plays a crucial role in understanding this balance. The Hubble constant, which measures the rate of this expansion, is another example of fine-tuning. If the expansion rate were different, galaxies might not have formed, or the universe could have expanded too quickly for life to develop. Galaxy clusters, large groupings of galaxies, formed under specific conditions. The universe's cooling, density fluctuations, and the influence of dark matter all contributed to the formation of these clusters. The precise balance of gravitational forces and the expansion rate was necessary for galaxy clusters to form. Our local group, the cluster of galaxies that includes the Milky Way, is a product of this finely tuned process. The formation of the Milky Way galaxy was a complex process influenced by the collapse of gas clouds, rotation, and the role of dark matter halos. The specific conditions that allowed the Milky Way to develop its spiral structure and habitable zones are examples of the universe's fine-tuning. Within the Milky Way, the solar system formed under very particular conditions. A protoplanetary disk, the role of supernova in seeding heavy elements, and the stability of the Sun all contributed to the formation of the solar system. The Sun's stable output, the position of the solar system within the Milky Way, and the specific conditions that led to the formation of planets highlight the fine-tuning necessary for our existence. Earth's formation required the accretion of planetary material, the presence of water, and the role of the Moon in stabilizing Earth's tilt. The right distance from the Sun, within the habitable zone, the presence of a magnetic field to protect against solar radiation, Jupiter's role in shielding Earth from asteroid impacts, and the right atmospheric composition for life are all examples of fine-tuning that made Earth hospitable for life. The emergence of life on Earth depended on a precise set of conditions. Liquid water, the right chemical elements, and a stable climate were essential. The formation of complex organic molecules and the development of life-supporting ecosystems required a finely tuned environment. From single-celled organisms to complex multicellular life, the evolution of life involved genetic mutations and natural selection, processes that were only possible in a finely balanced environment. Why the stars burn at the perfect rate, why atoms form the way they do, or why the cosmos didn't collapse in on itself shortly after the Big Bang. These are some of the questions that have led to the intriguing concept of the universe being fine-tuned. The idea of fine-tuning suggests that the fundamental constants and quantities in the universe are precisely set in such a way that allows life to exist. Think of it like tuning an old-fashioned radio. You need to get the dial exactly right to catch the station. If you're even slightly off, all you get is static. Similarly, if the universe's parameters were even slightly different, life as we know it wouldn't be possible. This concept took root in the mid-20th century, thanks to the work of physicist Fred Hoyle. In the 1950s, Hoyle was studying how carbon, an essential element for life, is synthesized in stars. He discovered that the production of carbon depends on a very precise resonance level in the carbon nucleus. If this resonance level were just a little different, carbon wouldn't form, and life wouldn't exist. Hoyle famously remarked that the universe seemed to be a put-up job, suggesting that it appeared designed for life. Since Hoyle's time, scientists have identified numerous other examples of fine-tuning. For instance, the strengths of the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are delicately balanced. If the gravitational force were a tiny bit stronger, stars would burn out too quickly for life to develop. If it were weaker, stars might not ignite at all. The electromagnetic force, which governs the chemistry of atoms and molecules, also has to be just right. If it was slightly different, the bonding of atoms would be impossible, and complex molecules essential for life couldn't form. The fine-tuning extends to the initial conditions of the universe. The Big Bang, the event that brought the universe into existence, had to be incredibly precise. The density of the universe had to be balanced to 1 part in 10 to the power of 60. To put that into perspective, it's like having a ruler stretching across the entire observable universe, divided into 1-inch increments, and the initial density of the universe had to be correct to within 1 inch. If it were off by that minuscule amount, the universe either would have collapsed back on itself or expanded too rapidly for galaxies, stars, and planets to form. One of the most striking examples of fine-tuning involves the cosmological constant, which drives the accelerated expansion of the universe. The value of this constant is extraordinarily small, yet non-zero. If it were much larger, the universe would have expanded too quickly for galaxies to form. If it were negative, the universe would have collapsed back into a singularity. The cosmological constant's value is fine-tuned to about 1 part in 10 to the power of 120, a level of precision that boggles the mind. So, why is the universe so precisely configured to support life? One explanation is the Anthropic Principle, which states that we observe the universe to be fine-tuned, because if it weren't, we wouldn't be here to observe it. In other words, the universe must have the properties necessary for life, because we are here to notice them. This idea first began to take shape in the mid-20th century, when physicists and cosmologists started grappling with the puzzling observations of how finely tuned various fundamental constants and quantities in the universe seem to be. One of the key figures in developing the Anthropic Principle was the physicist Robert Dicke. In the 1960s, Dicke argued that the conditions we observe in the universe must be compatible with the existence of observers. This line of thinking was later formalized by Brandon Carter, a British physicist, in 1973. Carter introduced the Anthropic Principle during a conference celebrating Copernicus's 500th birthday. He proposed two forms: the weak Anthropic Principle and the strong Anthropic Principle. The weak Anthropic Principle suggests that we must take into account the fact that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. In other words, the universe's laws and constants appear fine-tuned for life because, if they weren't, we wouldn't be here to notice them. This principle is largely observational and doesn't imply anything beyond the fact that we exist in a universe that allows us to exist. The strong Anthropic Principle, on the other hand, goes a step further. It suggests that the universe must have properties that inevitably lead to the development of intelligent life. This version implies a sort of necessity or purpose to the universe's life-permitting conditions. Some interpretations of the strong Anthropic Principle even suggest that the universe is somehow compelled to develop life and observers. One way to think about the Anthropic Principle is to imagine a lottery with an astronomical number of tickets. The fact that you have the winning ticket means that, out of all the possible outcomes, the one that allowed you to win is the one you experienced. Similarly, out of all the possible ways a universe could be configured, we find ourselves in one that supports life, because only such a universe could contain observers like us. The Anthropic Principle has sparked much debate and discussion among scientists and philosophers. One of the main points of contention is whether it provides a satisfactory explanation for the fine-tuning of the universe, or if it merely states the obvious, that we observe a life-friendly universe because we are here to observe it. However, critics argue that it doesn't truly explain why the universe has these properties, but rather just reframes the question. In the other hand, supporters of the Anthropic Principle argue that it offers a useful framework for understanding why the universe appears as it does. It aligns with the multiverse theory, which posits that there could be a vast number of universes, each with different physical constants and laws. Most of these universes wouldn't support life, but we find ourselves in one that does. In this context, the Anthropic Principle provides a lens through which we can make sense of the fine-tuning without invoking a higher purpose or design. The history of the multiverse idea can be traced back to various sources. One early form of the multiverse was suggested by the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett III in 1957. Everett's interpretation posits that all possible outcomes of quantum measurements actually occur in separate branching universes. This was a radical departure from the traditional view and laid the groundwork for thinking about multiple universes. The notion of a multiverse was further developed in the context of inflationary cosmology. In the early 1980s, physicists Alan Guth, Andre Linde, and others proposed the theory of cosmic inflation, which posits a rapid exponential expansion of the universe shortly after the Big Bang. This inflationary period could create vast regions of space that are causally disconnected from each other, effectively forming separate pocket universes with their own distinct properties. Linde, in particular, became a prominent advocate for the multiverse, suggesting that eternal inflation could lead to an infinite number of these pocket universes. Supporters of the multiverse theory argue that it elegantly solves the fine-tuning problem. If there are countless universes with varying constants and laws, then it is not surprising that at least one would have the right conditions for life. We exist in that universe because it is one of the few where life is possible. This shifts the question from, why is our universe fine-tuned for life, to how many other universes are there? Critics, however, raise significant objections to the multiverse theory. One of the main criticisms is that it is inherently untestable. By definition, other universes in the multiverse are causally disconnected from ours, meaning we cannot observe or interact with them. This makes the theory difficult, if not impossible, to verify through empirical evidence, which is a cornerstone of the scientific method. Some critics argue that this relegates the multiverse to the realm of philosophy rather than science. Despite these criticisms, the multiverse theory has provided deep insights and spurred considerable research and discussion. It challenges our understanding of reality and pushes the boundaries of what we consider possible. It also dovetails with other advanced theories in physics, such as string theory, which suggests that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings. String theory, with its complex mathematical framework and extra dimensions, provides a fertile ground for multiverse concepts. It suggests that different ways of compactifying these extra dimensions could lead to different physical laws and constants, potentially giving rise to a multiverse. As researchers delve deeper into string theory, they uncover more about its implications for the nature of reality and the potential existence of multiple universes. String theory is one of the most fascinating and ambitious theories in modern physics. It offers a potential theory of everything, aiming to unify all fundamental forces of nature into a single framework. At its core, string theory proposes that the most basic building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny, one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the particles and forces we observe. The origins of string theory date back to the late 1960s, when physicists were trying to understand the strong nuclear force, which holds atomic nuclei together. Initially, string theory was developed to explain certain properties of hadrons, the particles that make up protons and neutrons. However, it soon became clear that the theory had far-reaching implications beyond just describing the strong force. In the 1980s, it evolved into a potential framework for unifying all fundamental interactions, including gravity, which had eluded a quantum description for decades. The most striking implication of string theory is the need for multiple dimensions. While we experience the world in 3 spatial dimensions and one time dimension, string theory requires additional spatial dimensions, up to 10 or even 11 in some versions. These extra dimensions are compactified, meaning they are curled up so tightly that they are not perceptible at our macroscopic scale. The idea of extra dimensions might sound strange, but it helps solve many problems in theoretical physics, including the infamous issue of quantum gravity. String theory also offers an intriguing way to account for the fine-tuning of the universe. According to the theory, the way these extra dimensions are compactified determines the physical constants and laws of our universe. This leads to the concept of the string landscape, a vast array of possible configurations, each corresponding to a different universe with its own unique set of physical constants. If there are a multitude of possible universes, the fact that we find ourselves in one that is finely tuned for life could simply be a matter of statistical probability. Out of the potentially vast number of universes in the string landscape, at least a few would have the right conditions for life to emerge. Despite its elegance and potential, string theory is not without controversy. One of the main criticisms is its lack of empirical evidence. So far, string theory remains a highly mathematical construct without direct experimental confirmation. This has led some physicists to question whether it is truly a scientific theory in the traditional sense, as it currently cannot be tested or falsified through experiments. The mathematical complexity of the theory also makes it difficult to derive clear, testable predictions. Another point of contention is the sheer number of possible solutions within the string landscape. While this might explain fine-tuning, it also raises the issue of predictability. If there are so many possible universes, how can we determine which one corresponds to our own? This challenge has led to debates about the philosophical implications of the theory and whether it can ever provide definitive answers about the nature of our universe. As we explore the boundaries of string theory and ponder the intricate dance of vibrating strings that might unlock the secrets of the cosmos, we find ourselves confronted with even more profound questions about the nature of reality itself. One such idea that has gained traction in both scientific and philosophical circles is the simulation hypothesis, a theory that suggests our universe might be a sophisticated computer simulation created by an advanced civilization. The simulation hypothesis posits that what we perceive as reality is, in fact, an artificial construct, much like a computer-generated environment in a highly advanced virtual reality game. This idea, while seemingly outlandish at first glance, has a surprisingly robust foundation in both philosophical speculation and technological advancement. The concept was popularized in 2003 by philosopher Nick Bostrom, who presented a trilemma in his paper, "Are You Living in a Computer Simulation?" Bostrom argued that at least one of the following propositions must be true. Either almost all civilizations at our level of technological development go extinct before becoming capable of creating ancestor simulations, or if they do reach that stage, they are not interested in running such simulations, or we are almost certainly living in a computer simulation. The first part of the hypothesis, explaining it in detail, suggests that if an advanced civilization possesses immense computing power, it might be able to simulate entire universes with conscious beings who are unaware they are living in a simulation. These simulated beings would have experiences indistinguishable from those of beings in a real universe. The idea is grounded in the rapid advancement of technology particularly in fields like artificial intelligence and virtual reality. As our own capabilities in creating virtual worlds continue to grow, the leap to envisioning entire simulated universes doesn't seem as far-fetched. Supporters of the simulation hypothesis argue that the computational resources required to simulate a universe might not be as prohibitive as they first appear. If we assume that advanced civilizations have harnessed technologies far beyond our current understanding, the idea of simulating not just a planet or a galaxy, but an entire universe becomes conceivable. They point to the exponential growth in computing power and the potential for future breakthroughs in quantum computing as evidence that such simulations could be possible. On the other hand, critics of the simulation hypothesis raise several important objections. One major criticism is the lack of empirical evidence. Unlike theories in physics such as string theory, which can be explored through complex mathematical models, the simulation hypothesis remains largely speculative. There is currently no way to test or falsify the idea that we are living in a simulation. This has led some to dismiss it as an interesting philosophical exercise, rather than a serious scientific theory. Another argument against the simulation hypothesis is the base reality problem. If our universe is a simulation, then what about the universe of the beings who created the simulation? Are they also living in a simulation? This leads to an infinite regress, with each simulated universe potentially containing its own simulated universes and so on. This complexity raises questions about the likelihood and practicality of an original base reality existing somewhere up the chain. Philosophically, the simulation hypothesis has profound implications for our understanding of reality. If we are living in a simulation, it challenges our notions of existence, consciousness, and the nature of the universe. It raises questions about free will, the meaning of life, and our place in the cosmos. The fine-tuning of the universe, often cited as evidence for intelligent design or multiverse theories, could be explained as the parameters set by the creators of the simulation to ensure its stability and functionality. One of the most intriguing aspects of the simulation hypothesis is its potential to unite various theories and observations that currently seem disparate. For instance, the seemingly arbitrary constants in physics might be the result of choices made by the simulators. The strange behaviors observed in quantum mechanics, such as particles being in multiple states at once, could be understood as limitations or features of the simulation's computational framework. Just as string theory shatters our understanding with the notion of hidden dimensions and multiple universes, the simulation hypothesis dares us to consider that our entire reality might be an intricate, artificial construct. But who is the mastermind behind this elaborate design? This question brings us to the concept of intelligent design, a theory suggesting that the universe and living organisms are best explained by an intelligent cause, rather than undirected processes such as natural selection. The theory of intelligent design rests on the core idea that certain features of the universe and living beings are best explained by an intelligent cause. This concept hinges on the perceived inadequacies of naturalistic explanations, particularly Darwinian evolution, to account for the complexity and functionality observed in biological systems. Proponents argue that natural selection, random mutations, and other evolutionary mechanisms fail to explain the intricate details of cellular structures, the information-rich sequences of DNA, and the fine-tuned constants of the cosmos. Historically, the roots of intelligent design can be traced back to ancient philosophical thought. In ancient Greece, philosophers like Plato and Aristotle contemplated the existence of a purposeful order in the universe, setting the stage for later design arguments. Plato, in his dialogues, particularly the Timaeus, introduced the idea of a demiurge, a divine craftsman who shapes the cosmos according to an intelligible blueprint. This demiurge did not create matter from nothing, but ordered pre-existing chaotic matter into the structured universe we observe. Plato's demiurge is a benevolent figure, aiming to create a cosmos that reflects order, harmony, and purpose, mirroring the ideal forms, which are perfect, immutable archetypes existing in a non-physical realm. Aristotle, Plato's student, diverged from his teacher by emphasizing empirical observation and logical deduction. In his work, Metaphysics, Aristotle proposed the concept of the unmoved mover, an essential principle that causes motion and change in the universe without itself being moved. This unmoved mover, which Aristotle equated with God, is pure actuality, devoid of potentiality, and serves as the ultimate cause of all motion and change. Unlike Plato's demiurge, Aristotle's unmoved mover is not a creator in the sense of actively designing the universe, but rather an eternal, unchanging principle that imparts purpose and direction to all things. This idea laid a foundational stone for later arguments that perceived purpose and direction in the natural world as indicators of a designing intelligence. In the medieval period, Christian theologians and philosophers took these classical notions and wove them into a theological framework that sought to reconcile faith with reason. St. Augustine of Hippo, one of the early church fathers, integrated Platonic ideas into Christian doctrine. Augustine believed that God's creation was inherently good and purposeful, reflecting divine order and rationality. He saw the patterns and regularities in nature as manifestations of God's eternal ideas, which exist in the divine intellect, an interpretation resonating with Plato's realm of forms. The most influential figure in the medieval synthesis of classical philosophy and Christian theology was undoubtedly Thomas Aquinas. In his monumental work, Summa Theologica, Aquinas systematically presented arguments for the existence of God, including the famous 5 ways. Among these, the 5th way, known as the teleological argument or the argument from design, holds significant importance in the context of intelligent design theory. The teleological argument posits that the natural order and purposeful behavior observed in the world suggest the presence of an intelligent designer. This line of reasoning is based on the observation that inanimate objects which lack intelligence act towards an end or purpose. Aquinas argued that this purposeful action implies the guidance of an intelligent being. Aquinas noted that many natural phenomena exhibit regularity and order that cannot be attributed to chance. For instance, the way in which planets orbit the Sun, the intricate structure of living organisms, and the complex ecosystems found in nature all point towards a purposeful arrangement. Aquinas believed that such orderliness and directionality in the natural world are indicative of a higher intelligence orchestrating these processes. One of Aquinas' key observations was that inanimate objects which inherently lack consciousness or intelligence still act in ways that achieve specific goals. For example, a seed growing into a plant, the gravitational pull of the Earth keeping objects grounded, or the regularity of seasons. These are all instances where non-intelligent entities consistently work towards specific outcomes. Aquinas argued that since these objects cannot direct themselves towards an end, there must be an external intelligent force guiding them. Aquinas' teleological argument is an adaptation of Aristotle's concept of the final cause, or telos. Aristotle identified 4 causes: material, formal, efficient, and final, that explain why a thing is the way it is. The final cause, or the purpose of something, was central to understanding its existence and behavior. Aquinas took this idea and integrated it with a theological perspective, positing that the final cause is ultimately directed by God, the supreme intelligent designer. According to Aristotle, everything in nature has a purpose or end goal. For instance, the final cause of an acorn is to become an oak tree. This concept of inherent purpose was foundational to his understanding of the natural world. Aquinas built upon this by arguing that the final cause observed in nature is not self-sufficient, but requires an intelligent designer to set it in motion and guide it. For Aquinas, the teleological argument had profound theological implications. By identifying God as the ultimate designer, Aquinas provided a rational basis for the belief in a purposeful and intelligent creator. This argument supported the view that faith and reason are not mutually exclusive, but complementary. It suggested that the natural world, when observed and analyzed, reveals the existence and attributes of God. Aquinas' argument implies that the complexity and order in the universe are not products of random chance, but of deliberate design. God, as the ultimate designer, is responsible for the purposeful direction of all natural processes. This view not only reinforced the belief in God's existence, but also his omniscience and omnipotence. By observing the natural world, one could infer the intelligence and power of the Creator. During the Renaissance and the Enlightenment, the design argument continued to evolve, adapting to new scientific discoveries and intellectual currents. The scientific revolution, with figures like Galileo, Kepler, and Newton, revealed a universe governed by precise mathematical laws. Many of these early scientists were devout Christians who saw their work as uncovering the divine order of creation. Isaac Newton, for example, saw the intricate laws of motion and universal gravitation as evidence of a rational designer. The design argument reached its zenith in the 18th century with William Paley, an English clergyman and philosopher. In his work, Natural Theology, Paley famously compared the complexity of living organisms to a watch, arguing that just as a watch's intricate design implies a watchmaker, so too does the complexity of nature imply a divine designer. Paley's watchmaker analogy became a central pillar of the teleological argument, emphasizing the apparent purpose and order in biological systems as evidence of intelligent design. However, the advent of Darwinian evolution in the 19th century posed significant challenges to the design argument, which had long been used to assert the necessity of an intelligent designer for the creation of complex life forms. The design argument, rooted in the idea that the complexity and order in nature suggest a purposeful creator, faced a paradigm shift with the introduction of Charles Darwin's groundbreaking theory of natural selection. Darwin's theory of natural selection provided a naturalistic explanation for the complexity and diversity of life. According to this theory, species evolve through gradual changes, driven by environmental pressures and genetic variation. In essence, organisms with traits better suited to their environments are more likely to survive and reproduce, passing on those advantageous traits to future generations. Over long periods, this process leads to the emergence of new species and the adaptation of organisms to their habitats. This revolutionary idea undermined the necessity of invoking an intelligent designer to explain biological complexity. Prior to Darwin, many scientists and theologians saw the intricate structures and functions of living organisms as evidence of deliberate design by a higher power. However, natural selection demonstrated that complex features could arise from simple beginnings through a process that did not require conscious intervention. Darwin's ideas, detailed in his seminal 1859 book On the Origin of Species, provided a naturalistic explanation for the complexity and diversity of life. According to this theory, species evolve through gradual changes driven by environmental pressures and genetic variation. In essence, organisms with traits better suited to their environments are more likely to survive and reproduce, passing on those advantageous traits to future generations. Over long periods, this process leads to the emergence of new species and the adaptation of organisms to their habitats. This revolutionary idea undermined the necessity of invoking an intelligent designer to explain biological complexity. Prior to Darwin, many scientists and theologians following Paley's reasoning saw the intricate structures and functions of living organisms as evidence of deliberate design by a higher power. However, natural selection demonstrated that complex features could arise from simple beginnings through a process that did not require conscious intervention. This naturalistic framework suggested that the apparent design in nature could be an emergent property of evolutionary processes rather than the product of a divine creator. The introduction of Darwinian evolution led to intense debates and a re-evaluation of the design argument. Proponents of evolution, such as biologist Thomas Henry Huxley, argued that natural selection provided a robust and testable mechanism for explaining the diversity of life, making the idea of an intelligent designer superfluous. Huxley, known as Darwin's bulldog for his vigorous defense of Darwin's theory, emphasized the power of natural selection to account for the complexity of life, without recourse to supernatural explanations. Critics, however, such as biologist and geologist Louis Agassiz, contended that certain complex biological structures and systems could not be adequately explained by gradual evolutionary processes, maintaining that these features still pointed to a designer. Despite ongoing debates, the theory of evolution has provided a framework to view the universe as a whole without invoking a divine being. It has prompted scientists and philosophers to seek natural explanations for phenomena that were once attributed to supernatural forces. By demonstrating that complexity and order can arise from simple natural processes, Darwinian evolution has encouraged a more secular understanding of the natural world. In this framework, the universe is seen as a dynamic system, governed by natural laws and processes. The diversity of life is a result of billions of years of evolutionary change, driven by natural selection, genetic drift, mutation, and gene flow. This perspective emphasizes the interconnectedness of all living things, highlighting the shared ancestry and common processes that unite the biological world. Moreover, this naturalistic worldview extends beyond biology to other scientific disciplines, fostering a comprehensive understanding of the cosmos. In physics, for example, the Big Bang theory provides a naturalistic explanation for the origin of the universe, while in geology, the theory of plate tectonics explains the movement of Earth's continents and the formation of various geological features. These scientific theories, like evolution, rely on natural laws and processes to explain complex phenomena without invoking supernatural explanations. Extending this framework, some scientists and philosophers have explored the idea of a Darwinian evolution of the universe. This concept applies evolutionary principles to the cosmos as a whole, suggesting that the universe and its fundamental properties may also be subject to a kind of natural selection. One such idea is the theory of cosmological natural selection, proposed by theoretical physicist Lee Smolin. According to Smolin, new universes are born through black holes, and each new universe has slightly different physical constants. Universes with properties conducive to the formation of black holes would produce more offspring, leading to a natural selection process favoring universes capable of generating black holes. This cosmological perspective suggests that the fundamental constants of nature, such as the strength of gravity or the charge of the electron, might be fine-tuned not by design, but by a natural selection process operating at the cosmic level. Just as biological evolution explains the adaptation and complexity of life, cosmological natural selection could explain the seemingly fine-tuned properties of our universe. In modern times, the intelligent design movement has gained prominent proponents, including figures like William Dembski and Stephen Meyer. These figures have been at the forefront of shaping and promoting intelligent design as a serious contender to the prevailing theory of evolution. Dembski, a mathematician and philosopher, developed the concept of specified complexity, which he argues is a hallmark of intelligent design. According to Dembski, specified complexity can be recognized when something is both complex, meaning it is not easily reproducible by chance, and specified, in that it matches an independent pattern or serves a specific function. He uses this framework to argue that naturalistic processes alone are insufficient to explain the intricate and purposeful arrangements found in biological systems. Stephen Meyer, a philosopher of science, has provided further support to the intelligent design argument through his work on the information content in DNA. In his influential book, Signature in the Cell, Meyer contends that the digital code embedded in DNA, a code that directs the assembly of proteins necessary for life, is best explained by an intelligent cause. Meyer argues that natural processes, such as random mutation and natural selection, do not adequately account for the origin of this complex information. He posits that the sudden appearance of vast amounts of specified information at the cellular level points to an intelligent source, much like how a software program necessitates a programmer. The modern intelligent design movement, as has previously mentioned, did not appear in a vacuum. It emerged from a long tradition of the design argument, stretching back to ancient philosophers and theologians who saw evidence of design in the natural world. The Enlightenment and subsequent scientific revolutions brought significant changes, but the argument persisted, evolving into its modern form largely as a response to Darwinian evolution. Unlike creationism, which directly invokes the biblical account of creation, intelligent design strives to present itself as a scientific hypothesis, albeit one that introduces a designer. One of the critical ideas proposed by ID advocates like Michael Bear is irreducible complexity. Bear, a biochemist, argues that certain biological systems, such as the bacterial flagellum, are composed of multiple, interdependent parts that contribute to the system's basic function. He claims that removing any one of these parts would cause the entire system to cease functioning, suggesting that such systems could not have evolved through successive, slight modifications as proposed by Darwinian evolution. Instead, Bear argues these systems must have been designed as fully functional units from the beginning. Despite these claims, the scientific community has largely rejected intelligent design, arguing that it lacks empirical support and does not provide a testable framework. For a theory to be scientifically valid, it must make predictions that can be empirically tested and potentially falsified. Critics point out that intelligent design does not offer specific predictions about biological phenomena that can be tested in the lab or field. Instead, it often critiques perceived gaps or shortcomings in evolutionary theory without providing a robust alternative explanation grounded in empirical data. Moreover, intelligent design is criticized for not adhering to methodological naturalism, the principle that scientific explanations should rely solely on natural causes. By positing an intelligent designer who operates outside the realm of natural law, intelligent design steps into the metaphysical, which is beyond the scope of scientific inquiry. This makes it difficult to test or falsify, leading many scientists to view it as a form of pseudoscience rather than a legitimate scientific theory. Philosophically, intelligent design faces challenges from principles like Occam's razor, which favors simpler explanations that make the fewest assumptions. Evolutionary theory, which explains the diversity of life through natural mechanisms like mutation, genetic drift, and natural selection, does not invoke an external designer and is thus considered a more parsimonious explanation. Intelligent design, by introducing the concept of a designer, adds an additional unobservable layer to the explanation of biological complexity, which critics argue is unnecessary and complicates rather than clarifies our understanding of life. The burden of proof is another significant philosophical hurdle for intelligent design. In scientific discourse, the burden of proof lies with those proposing a new theory. Intelligent design advocates assert that life's complexity necessitates a designer, yet they have not provided sufficient empirical evidence to substantiate this claim. Much of the argumentation for intelligent design focuses on critiquing evolutionary theory rather than building a positive case for design based on empirical research. The controversy surrounding intelligent design has also played out in legal and educational arenas. In the United States, the most notable case is Kitzmiller v. Dover Area School District in 2005, where a federal judge ruled that intelligent design is not science, but a religious view. The ruling concluded that it is unconstitutional to teach intelligent design in public school science classes, reinforcing the view that intelligent design lacks the scientific credibility and empirical support required to be part of the science curriculum. But even as the intelligent design movement presses on, there remains an intriguing conundrum that often goes unaddressed. The universe exhibits both perfect fine-tuning and profound imperfections. On one hand, the constants of nature are precisely calibrated to allow for the existence of life. From the exact force of gravity to the precise charge of the electron, The universe seems finely tuned to support complexity and consciousness. Yet on the other hand, this perfection is marred by significant cosmic imperfections. The universe is filled with chaotic phenomena such as black holes, gamma-ray bursts, and supernovae that can obliterate entire star systems. Additionally, the vast expanses of empty space and the presence of dark matter and dark energy add layers of mystery and unpredictability. If the universe is indeed designed by an intelligent agent, why does it exhibit such notable flaws? This duality raises questions about the nature of the designer and the purpose behind the universe's seemingly imperfect aspects. When we consider the vastness and complexity of the universe, it's tempting to think of it as a perfect entity, finely tuned and harmoniously balanced to support life and its myriad phenomena. However, upon deeper examination, we find that the universe is riddled with imperfections and anomalies. These imperfections are not flaws, but essential components that drive change, evolution, and the development of complexity. In this discussion, we will explore why the universe is considered perfect through its imperfections, focusing on the roles of dark matter and dark energy, the philosophical implications of imperfection, and how these elements shape our understanding and ethical considerations. Our current understanding of the universe includes a fascinating mixture of known and unknown components. Among the most enigmatic are dark matter and dark energy, which together comprise about 95% of the universe. Dark matter, which accounts for approximately 27% of the universe, is an invisible substance that does not emit, absorb, or reflect light. Its presence is inferred from its gravitational effects on visible matter, such as stars and galaxies. Dark energy, on the other hand, makes up about 68% of the universe and is believed to be responsible for the accelerated expansion of the universe. The distribution of dark matter and dark energy is far from uniform, leading to what might be perceived as an imperfect structure of the universe. Dark matter tends to clump together, creating gravitational wells that help to form galaxies and clusters of galaxies. This clumping is essential for the large-scale structure of the universe, as it provides the scaffolding upon which visible matter accumulates. However, the exact nature of dark matter remains a mystery, and detecting it directly has proven to be an immense challenge. Various experiments and observatories, such as the Large Hadron Collider and the Vera C. Rubin Observatory, are dedicated to uncovering its properties. But so far, dark matter has eluded direct observation. Similarly, dark energy poses significant observational challenges. It is thought to be a property of space itself, causing the universe to expand at an increasing rate. The distribution of dark energy is even less understood than that of dark matter, and its exact nature is one of the biggest open questions in cosmology. The apparent imperfections in our understanding and the distribution of these components highlight the limits of our current models and the complexity of the universe. These imperfections in the distribution of dark matter and dark energy have profound implications for cosmology. They affect our models of the universe's evolution and challenge our understanding of its ultimate fate. For instance, the baryon asymmetry problem, which refers to the imbalance between matter and antimatter in the universe, adds another layer of complexity. According to the Big Bang theory, matter and antimatter should have been created in equal amounts. Yet, we observe a universe dominated by matter with very little antimatter. This asymmetry is crucial for our existence, but remains an unresolved puzzle in cosmology. While the universe's imperfections may initially appear as flaws, they are actually essential for the dynamic processes that drive cosmic evolution. Imagine a universe where everything is perfectly balanced and uniform. Such a scenario would be eerily static, devoid of the complexities and changes that define our cosmos. It is these very imperfections, these slight deviations from perfect symmetry, that fuel the rich tapestry of cosmic development. Consider the early universe shortly after the Big Bang, when it was a hot, dense, and nearly uniform sea of particles. If it had been completely homogeneous, with no variations in density or temperature, gravity would have had nothing to act upon. There would be no denser regions for gravity to pull together, no seeds for stars and galaxies to form. However, the universe was not perfectly uniform. Tiny quantum fluctuations in the fabric of space-time created slight irregularities, regions just a bit denser than their surroundings. Over millions and billions of years, these denser regions attracted more matter through the force of gravity, gradually growing into the stars and galaxies we see today. This concept of imperfection extends beyond the initial conditions of the universe. Take, for instance, the formation of stars within galaxies. The interstellar medium, the vast space between stars filled with gas and dust, is far from uniform. Clumps of gas, often disturbed by the shock waves from supernova, can collapse under their own gravity to form new stars. These stars, in turn, can have planets orbiting them, some of which might be in the habitable zone where conditions are just right for life as we know it. None of this would be possible in a perfectly smooth universe. Furthermore, these imperfections are not just physical, but also temporal. The universe is constantly evolving, with stars being born and dying, galaxies merging and interacting, and black holes growing and affecting their surroundings. Each of these events introduces new imperfections, new asymmetries that drive further evolution and complexity. The death of a star, for instance, can lead to the creation of heavy elements that are essential for the formation of planets and life. Supernova, the explosive deaths of massive stars, scatter these elements across the galaxy, enriching the interstellar medium and paving the way for new generations of stars and planets. From a cosmological perspective, the irregular distribution of matter, the formation of galaxies, and the variations in the cosmic microwave background radiation are not just random quirks. They are fingerprints of the universe's history and its ongoing evolution. The cosmic microwave background, for example, reveals slight fluctuations in temperature that correspond to regions of varying density in the early universe. These density variations were crucial for the formation of galaxies, as gravitational forces caused matter to clump together over time, eventually forming the complex structures we observe today. Without these imperfections, the universe would be a homogeneous soup of particles, devoid of stars, planets, and life. In the natural world, imperfection is the bedrock of biological diversity and resilience. Genetic mutations, which might be seen as errors in the replication process, are actually the raw material for evolution. These mutations introduce variability into populations, allowing organisms to adapt to changing environments. This adaptability is evident in phenomena like antibiotic resistance in bacteria, where random mutations confer survival advantages under selective pressures. Environmental variations also play a crucial role in shaping ecosystems, creating diverse habitats that support a wide array of species. For example, the varying climates and terrains of Earth from arid deserts to lush rainforests, provide niches for different organisms to evolve and thrive. Adaptation and resilience stem from these biological imperfections. Life on Earth has endured and flourished through billions of years of environmental changes, from ice ages to asteroid impacts. This resilience is seen in the way plants and animals have developed mechanisms to cope with stress, repair damage, and exploit new opportunities. For instance, the ability of certain plants to go dormant during droughts, or the migration patterns of birds in response to seasonal changes, are examples of how life adapts to survive. These adaptations are a testament to the strength and creativity inherent in biological imperfections. Contemplating the universe's imperfections also encourages us to recognize and address our cognitive and cultural biases. Our interpretations of cosmological data are influenced by our limited perspectives and inherent biases. By acknowledging these biases, we can strive for more objective and accurate scientific inquiry. Different cultures and philosophies offer diverse interpretations of the cosmos, reminding us that our understanding is shaped by our backgrounds and experiences. Embracing this diversity of thought enriches our scientific endeavors and fosters greater acceptance of differing viewpoints, leading to a more holistic understanding of the universe. Recognizing the fragility and rarity of life in the vast cosmos underscores its intrinsic value. Life, with its delicate balance and complexity, is an extraordinary phenomenon. This recognition compels us to cherish and protect the conditions that allow life to thrive. On Earth, this means taking action to address environmental challenges like climate change, habitat destruction, and pollution. In the broader context of the universe, it calls for a respectful approach to space exploration, ensuring that our quest for knowledge does not harm potential ecosystems on other planets or moons. The ethical implications extend to our responsibility to nurture life wherever we find it. Understanding that we are stewards of not only our planet, but potentially other worlds as well. Thus, the imperfections of the universe are not shortcomings, but the very foundation of its dynamic nature. They challenge us to appreciate the complexity and beauty of existence, to strive for a deeper understanding, and to act with ethical consideration towards the world and the cosmos. These imperfections are the threads that weave the intricate and ever-evolving tapestry of the universe, inviting us to ponder our place within it and our responsibilities as inhabitants of this extraordinary realm. In our quest to comprehend the universe, we encounter the concept of fine-tuning, the remarkable alignment of physical constants and conditions that enable life as we know it. It speaks to a universe seemingly crafted with meticulous precision, fostering conditions where stars can form, planets can sustain life, and complex beings can ponder their own existence. This fine-tuning evokes a sense of awe and wonder, suggesting a cosmic blueprint or a guiding hand behind the scenes. Yet, alongside this apparent perfection lies imperfection, the irregularities, asymmetries, and unpredictabilities that permeate every corner of the cosmos. From the chaotic collisions of galaxies to the minute quantum fluctuations, these imperfections defy our neat theories and challenge our understanding. They remind us that the universe is not static, but fluid, not predictable, but endlessly surprising. Looking to the future, human understanding of these dual aspects, fine-tuning and imperfection, holds profound implications. Scientific discoveries continue to push the boundaries of our knowledge, probing deeper into the mysteries of physics, cosmology, and the origins of existence. Each revelation adds another layer to our comprehension, yet also reveals new questions, beckoning us further into the realms of exploration and inquiry. As we ponder these complexities, we are encouraged not only to marvel at the universe's intricacies, but also to engage in ethical reflection. Our awareness of fine-tuning invites us to consider our stewardship of this finely tuned planet and our responsibility towards its preservation. Simultaneously, the recognition of imperfection humbles our scientific hubris, reminding us of the limitations of our current understanding and the vastness of what remains to be explored. In conclusion, the future of human understanding lies in the delicate balance between embracing the marvels of fine-tuning and grappling with the enigmas of imperfection. It calls for continued curiosity, rigorous inquiry, and ethical awareness as we navigate the frontiers of knowledge. By doing so, we not only deepen our understanding of the universe, but also enrich our appreciation of our place within it, fostering a more profound connection to the cosmos and to each other.